Continuing on with the Chapter 2 lecture series, we're now going to be discussing acid-base chemistry, equilibrium, and pKa. So just as a refresher from general chemistry, in terms of acid-base chemistry, Bronsted acids are defined as an H plus or proton donor. Acids donate a proton to yield the conjugate base. So for example, in this case, this acid is donating a proton, and as a result, the acid gets converted to the conjugate base. A Bronsted base is a proton acceptor. Bases gain a proton to yield the conjugate acid. So for example, this base in this case accepts a proton from the acid and in turn gets converted to the conjugate acid. Now, let's talk a little bit about equilibrium in the context of weak acids and weak bases. Weak acids undergo reversible dissociation in solution to yield the conjugate base and H+. Weak acids and weak bases will react with solvents such as water reversibly. So for example, if you have a weak acid, its dissociation is reversible. This is an equilibrium process. So if you have a weak acid and a weak base, they will react with solvents such as water reversibly. Now, the degree of reversibility depends a little bit on the exact acid and base that you're dealing with. The acid equilibrium constant, Ka, measures the ratio of H plus and conjugate base to starting acid. Ka, or a general equilibrium expression, is essentially the ratio of the concentration of products over the concentration of reactants. The larger your Ka value, the more H plus, and in addition to having more H plus, the more conjugate base you have present. Now, in terms of pKa and pKb, pKa is a measure of acid strength. Strong acids have small negative pKa values, more H plus in solution. So pKa is defined as the negative log of Ka. The more negative your pKa value, the larger your Ka value, the more H plus and A minus are present in solution. pKb is a measure of base strength. Strong bases have small negative pKb values, implying there's more hydroxide in solution. So for example, if we have a base can react with water to generate the conjugate acid, as well as hydroxide. Now, pKa and pKb are related by the solvent constant. In water, this is known as Kw. Ka times Kb is equal to Kw. And the Kw for water in this case is about 1 times 10 to the negative 14th molarity squared, though this depends a little bit on temperature. Let's now talk a little bit about acid strength and pKa. pKa is a measure of acid strength. Strong acids have small or negative pKa values, implying that there's more H plus in solution. So for example, HI is a strong acid with a pKa value of negative 10. Acetic acid is a reasonably strong acid for an organic compound with a pKa of 4, while an alcohol with a pKa of 17 is a relatively weak acid. The pKa value provides us a measure of acid strength. The smaller and more negative your pKa value, the stronger your acid. So if we had to rank the following substances in order of increasing acidity given the pKa values, generally, the lowest and smallest pKa value will be the strongest acid. So acetic acid would be the most acidic, then pentanedione, then phenol, and finally acetone. we're essentially using the pKa values to rank the compound acidity. Acetic acid with the smallest pKa value is the most acidic, while acetone with the largest pKa value is the least acidic. Remember, Ka is proportional to the concentration of H+, and pKa is the negative log of Ka. In other words, Ka is 10 to the negative pKa. So, the smaller and more negative your pKa value, the larger your Ka value, and thus the more H+ we have in solution, and thus the stronger an acid we're dealing with. Let's talk now about pKa and pKb. The pKa of an acid and the pKb of its conjugate base are inversely proportional, where pKa is proportional to 1 over pKb. This leads to the following saying that's very helpful. Strong acids produce weak conjugate bases, while weak acids produce strong conjugate bases. So in this case, if we have HI, which is a strong acid, it reacts in order to yield a conjugate base that's very weak. By the same token, if you have a weak acid such as methanol, it reacts to yield a relatively strong conjugate base. So let's apply what we've learned here, and we're asked which of the following anions is the strongest base. We're given the pKa values for the parent acid, and in turn, we can use that to figure out the pKb values for the conjugate base. So in this case, let's calculate our Kb, given that Kb is proportional to 1 over Ka. So we're approximating this here. So here we have 1 over 19 versus 1 over 9. Okay, so as we can see here, this compound, which has a pK of 9, is the stronger acid, which in turn means this is the weaker base. The weaker acid produces the stronger base. So as you can see, this would be the strongest base. So in order to identify the strongest base, if you know the parent acid, you look at the pKa, the strongest parent acid makes the weakest conjugate base. The weakest parent acid makes the strongest conjugate base. Okay. I'd now like you to take a look at the following reference. This is the Evans pKa table, and there are variations of this found on Canvas and online. And this contains the common pKa values for a range of different functional groups. I'd like you to be familiar with this pKa table, as we'll be using it to solve future problems. So don't hesitate to reference these pages as we progress through the rest of this lecture. I've also provided you some common intermediate ion pKa values just for your reference, as these are common intermediates that are generated during organic reactions. Okay, to make sure that we're comfortable using pKa tables, let's look at an example where we apply our pKa table. So in this case, we're given the structure for L-DOPA, and we're asked to identify the 4 most acidic protons in the compound. We're then asked to arrange those protons in order of increasing, one moment. We're then asked to arrange those protons in order of increasing acidity. So I'd like you to pause the video at this time. You can reference the pKa table provided, and then we'll discuss this example momentarily. Okay, so first and foremost, we have a carboxylic acid proton. This has a pKa of around 4.7. We have two phenol protons, which have a pKa of about 9. To show where we're getting these values from, first and foremost, carboxylic acid is around 4. And for the phenol, even though it's not in this table, there are also some additional tables found in your book that have the phenol pKa values tabulated. We also have an amine, which has a pKa value of about 35, 33. See that right here. Okay, so we've identified the four most acidic protons, and we can arrange those protons in order of increasing acidity. The carboxylic acid proton is going to be the most acidic with a pKa value of around 4.7. The two phenol protons are pretty close to equivalent. We'll use an equal sign. And then the amine proton is going to be the least acidic. One thing that's pretty interesting about this problem is even if you just found the alcohol pKa value, you'd still be able to get this same relative ranking. For those curious as to why the phenol protons are a little more acidic than a traditional alcohol, we'll actually be talking about that momentarily. So again, if you can recognize different functional groups, you can then recall the pKa value for that functional group and then rank protons in terms of their relative acidity. Now, one thing that we can also do with pKa values is that we can predict the outcome of acid-base reactions. So in acid-base reactions, the acid reacts with the base to yield the conjugate acid and conjugate base. So for example, if we have an acid-base reaction between water and ammonia react, the base accepts a proton, the acid donates a proton, and that in turn yields the conjugate acid from the base, and the acid, when it loses a proton, yields the conjugate base. These reactions are reversible. So just as easily, in the reverse reaction, the conjugate acid and conjugate base can react to yield the parent acid and parent base. Now, the real question is, how do we know which of these two reactions is favored? Is this reaction going to be forward, product favored, or reverse, reactant favored? Well, the overall reaction equilibrium constant can be determined through the ratio of the Ka of the reactant acid and the conjugate acid. The overall reaction pK equilibrium can be determined by taking the pK of the reactant minus the pK of the product acid. In other words, if the reaction K equilibrium is greater than 1, the reaction is product favored. If K equilibrium is less than 1, then the reaction is reactant favored. If the reaction pK reaction is less than 1, the reaction is product favored. If pK reaction is greater than 1, the reaction is reactant favored. So, in order to determine the directionality of an acid-base reaction, we look at the pKa of the starting acid and the conjugate acid. We then take the difference between pKa values. If the difference is less than 1 or less than or negative, then the reaction is product favored. If it's greater than 1 or positive, then the reaction is reactant favored. Let's look at an example. So here we have the following reaction. We have the pKa of the starting acid and the pKa of the conjugate acid. Let's take the delta pKa, the difference between the pKa values of the reactant and product. So we're going to take 9, which is our reactant pKa, and subtract the product pK. So 9 minus 15.7 gives us negative 6.7. As delta pK is less than 1, this reaction is product favored. In other words, when you look at an equilibrium, the equilibrium will favor production of the weaker acid and favor production of the more stable, weaker conjugate base. So if we're drawing these equilibrium arrows, we draw more towards the products than towards our reactants. Let's look at another example. So I'd like you to try this one. So pause the video and give an attempt at this following problem. Is the following reaction reactant or product favored? Use your pKa table for this. So in this case, we have a proton transfer. You can think of this fundamentally as an equilibrium between a carboxylic acid and an amine reacting to yield carboxylate and an ammonium salt. With this information in mind, take a few moments, look up the pKa values, and I'd like you to tell me whether this reaction is reactant or product favored. Okay, so first and foremost, we have a carboxylic acid with a pKa of around 4.7, give or take. The protonated amine has a pKa of around, not 35, this is a protonated amine, between 9 and 11. So we have our parent acid, we have the conjugate acid. So if we take the difference in pKa values, we have 4.7 minus 9, that gives us negative 5.7. As this difference in pKa is less than 1, this tells us that the equilibrium is product favored. This is pretty relevant in terms of biological systems, in that when we look at this compound, which is known as an amino acid, amino acids actually exist in the following form, which is known as a zwitterion, where we have both a negatively and positively charged atom in this structure. The reason why this occurs, the carboxylic acid is a strong acid, it can protonate the amine, and the conjugate ammonium salt generated is a weaker acid. The equilibrium favors production of the weaker, more stable conjugate acid, and additionally, it favors production of the weaker, more stable conjugate base. We can figure that out looking at the difference in pKa values. Okay, so as you've seen, we can use pKa values and the difference between the reactant and product acid pKa values to determine whether a reaction is reactant or product favored. Let's take a look now at some anion stability trends. The reason why we're going to need to be familiar with anion stability trends is that we can use these trends to get a sense on whether an acid-base reaction is reactant or product favored. So if we don't have pKa values, one other tool that we can use to determine whether an acid-base reaction is reactant or product favored is by looking at the stability of the parent base and the conjugate base anion. So let's talk about stability trends for anions and other conjugate bases. So strong acids react to yield weak, stable conjugate bases, while weak acids yield unstable conjugate bases. To compare the strength of two acids, we can compare the stability of the conjugate base of each acid. So let's talk about some factors affecting conjugate base and anion stability. Anions are generally stable on large electronegative atoms. So for example, as you increase atom electronegativity, your overall conjugate base stability increases and the acid strength increases. So as you can see, if we have a stable conjugate base, we have a stronger acid. So the more stable your conjugate base, the stronger your parent acid. So let's try to apply what we've learned in terms of atom trends. So we have 3 protons. Which of the following protons is most acidic? So we want the largest, most electronegative atom, and that is going to be the atom attached to sulfur. Because sulfur is large and it's electronegative. That means that the conjugate base anion generated by pulling off this proton, this is a stable anion because we're placing the negative charge on a large and importantly, very electronegative atom. So if we had to do a ranking, this is the most acidic, the proton attached to the nitrogen is the next most acidic, and the proton attached to carbon is the least acidic. This also matches the pKa values that we've looked at previously. So everything's making sense so far. We're next asked to compare which of the following 2 compounds is more acidic. So in this case, we have an alkane and we have an alcohol. Looking at the conjugate base anion, we're placing a negative charge on carbon versus oxygen. In this case, oxygen is far more electronegative. This conjugate base is more stable, and as a result, the parent acid is more acidic. This matches what we've seen in terms of pKa's. The alcohol pKa is around 17, while an alkene has a pKa of around 50. The second major factor affecting anion stability is conjugation. Anions are stabilized via conjugation, especially conjugation with electronegative atoms. For example, if we compare an alcohol versus a carboxylic acid, an alcohol has a pKa of 17, while a carboxylic acid has a pKa of closer to 4 to 5. The reason being is that the anion generated from the carboxylic acid can be delocalized. This is a delocalized and stable anion. One thing I'd like to draw your attention to is that in the carboxylic acid, this anion is not just stabilized via conjugation to any atom, it's especially stabilized because we can distribute this negative charge across a large number of electronegative atoms in particular. So, when in doubt, you'll want to consider and draw the conjugate base anion. So let's do some examples. So which of the following protons in each compound is most acidic? So here we have a allylic versus a vinylic hydrogen. So in this case, if we compare the 2 possible conjugate base anions, we have the following anion versus this vinylic anion. As you can see, one of these anions can be delocalized. And as a result, this anion is more stable. As a result, this proton would be most acidic. Generally, allylic protons are more acidic than vinylic protons. Let's look at this second case. Here we have 2 hydrogens. One is a phenol or a phenolic hydrogen, the other is an alcohol. Now, if we think about which of these protons are going to be more acidic, we again have to look at the conjugate base anion. So if we pull off this proton, we have the choice between the following conjugate base anions. I'm just drawing them both on the same molecule for comparison. Let's just look at the conjugate base anion of deprotonating the phenolic hydrogen. As you can see, this lone pair is conjugated to our aromatic ring, and thus it can be delocalized. Thus, because this specific conjugate base is especially stable, this phenolic hydrogen is the most acidic hydrogen. I'd like you to take what we've learned from these prior two examples and apply it to this next problem, keeping in mind that anions are especially stable if they're conjugated to electronegative atoms. So take a few moments to work on that, and then we'll discuss. So in this case, we have a phenol versus a carboxylic acid. The phenol would generate a conjugate base anion that is conjugated to the aromatic ring. So we can distribute this negative charge across our carbon atoms in this ring. By comparison, the carboxylic acid, if deprotonated, generates a carboxylate conjugate base, and we can delocalize this negative charge across these electronegative oxygen atoms. Looking at pKa values, a carboxylic acid has a pKa of around 4, while a phenol has a pKa of around 9. Part of the reason why this carboxylic acid proton is so much more acidic is that it's also a delocalized, the conjugate base is stabilized because we can delocalize that electron density across multiple atoms, but we're specifically delocalizing that electron density across electronegative oxygen atoms. The more electronegative your atom, the more readily able it is to stabilize a negative charge and stabilize the conjugate base anion. Okay, so we've seen that by drawing out the conjugate base anion, we can in turn compare and rank protons based on their relative acidity. You don't need to necessarily have a full set of pKa values. You can compare and contrast the conjugate base anions and use these stability rules to compare and rank compounds based on acidity. Let's talk about some additional effects. One example would be inductive effects. So anions are stabilized by adjacent electron withdrawing groups. This is known as an inductive withdrawing group. Induction is this idea that electronegative atoms draw electron density from atoms bonded to that atom and adjacent bonded atoms. So for example, if we look at trichloroacetic acid, these chlorine atoms pull electron density away from their attached carbon. And as a result, this in turn pulls electron density away from the adjacent attached oxygen and the adjacent attached oxygen-hydrogen bond. So as a result, when you have more electron withdrawing groups, that increases the acidity of adjacent protons. So for example, if we look at trichloroacetic acid, it is much more acidic due to these inductive withdrawing effects. Why is that? Well, if we look at the conjugate base, so let's just put the more acidic label here, because trichloroacetic acid is much more acidic than normal just hydrogen substituted acetic acid. And part of the reason for that is these inductive withdrawing groups stabilize your anion because we're pulling electron density from the adjacent carbon atoms and from that anion, and that helps stabilize the anion. So as you can see, when you have inductive withdrawing groups, this has a pretty notable effect on your proton acidity. Inductive effects are stronger the more withdrawing groups are present, And the stronger the withdrawing group, and the closer the withdrawing groups are to the anion. So for example, as we continue to add chlorines, add inductive withdrawing groups, that in turn increases the inductive withdrawing effect. And as a result, the more inductive withdrawing groups you have adjacent to your proton, the more acidic your proton will become because the conjugate base is going to be more stable. By the same token, if you start to move your withdrawing group farther and farther away from your acidic proton, that in turn decreases the acidity. In order for an inductive withdrawing effect to be strongest, you want your withdrawing group as close to the acidic proton as possible. So, to this end, let's work on these two examples where we're asked to identify the most acidic proton in this molecule and identify which of the following two molecules is most acidic. So let's take a few moments to work on that and then we'll discuss. So in this case, we have two protons. They're both attached to alcohols. However, one of them is adjacent to these withdrawing groups. As a result, the proton attached to the alcohol closest to these withdrawing groups is going to be more acidic. This is an example of proximity effects. In this second case, we have bromoacetic acid versus dibromoacetic acid. The more inductive withdrawing groups we have, the more acidic our proton will be. The next effect we have to consider, and this one's pretty interesting, is this idea of orbital effects. Anions are more stable if the electrons are placed in a lower energy orbital. Lower energy hybrid orbitals have more S character, with the sp hybrid orbitals being the lowest in energy and the sp3 being higher in energy. This makes sense. As you can see, alkynes are most acidic because this lone pair is held in an sp orbital. Alkenes are the next most because the lone pair is for the conjugate base is held in an sp2 hybrid orbital. And alkanes are the least acidic because when you generate the conjugate base, the lone pair is held in an sp3 orbital. For alkynes, when you deprotonate them, you generate the most stable anion possible for a carbon-centered anion. Well, for alkanes, you'll get the least stable anion. So in this case, we have an example where we're asked to rank which protons are more acidic. I'll do the first one, you'll do the second one. So in this case, we have a proton attached to an alkyne, which is an sp hybridized carbon, versus an alkene, which is an sp2 hybridized carbon. As we discussed, the conjugate base anion is more stable if the lone pair is placed in a lower energy orbital. sp orbitals are lower in energy, and thus the parent acid for a carbon hydrogen bond, this proton attached to an sp hybridized carbon is going to be the most acidic or more acidic compared to an sp2 carbon hydrogen bond. Let's look at this next case. Here we have a bunch of alkanes and an alkyne proton. As we discussed, protons attached to sp3 carbons aren't particularly acidic, even though this hydrogen in red, you do have the potential to get a resonance stabilized anion. It's still not ideal. The proton held in an sp hybrid orbital is generally going to be lower in energy, and so the lone pair held in an sp hybrid orbital is going to be lower in energy, and thus this alkyne proton is going to be the most acidic proton. So this is an example of how hybridization and orbital effects can impact proton acidity. Let's talk a little bit about some factors that influence anion stability and this idea of resonance donors and acceptors and this idea of inductive and resonance effects. So substituents exert both inductive and resonance effects. A resonance donor is a substituent that donates electron density via resonance to conjugated atoms. Strong donors include amines, alcohols, ethers, amides, and esters, while weak donors include alkyl and aryl groups. Why is this important? Resonance donors destabilize anions that are conjugated, leading to a less acidic proton. To see what's happening here, let's look at what happens in the following molecule. In this case, we have an ester, and here we have a donor group. This OR group has a lone pair that we can use to donate electron density into adjacent atoms. Why is this a problem? Well, if we look at the conjugate base for a moment, we can see that for our conjugate base anion, one of the reasons why this conjugate base anion can be stabilized is via pushing electron density into the adjacent pi bond. However, this resonance donor, this OR group here, is also trying to push electron density into that pi system. So, because this donor is pushing electron density into this pi system, this destabilizes our anion. It's almost like the opposite idea to why inductive withdrawing groups increase proton acidity. In this case, we have this electron-rich conjugate base anion, and we're continuing to shove electron density into our pi system. This destabilizes our conjugate base anion, and as a result, it makes this proton less acidic. As you can see, when we went from an alkyl group to an OR group, an ether group, the ether group is a much better donor of electron density. It is a resonance donor. And as a result, this resonance donor destabilizes the conjugate base anion. Looking at amides here, if we look at the pKa of an amide, it's closer to 30 to 35. It's much higher than that of an ester. The reason being, this nitrogen is a great donor. And in turn, what that means is that your proton is less acidic. Anytime you have resonance donors pushing electron density into adjacent atoms near our conjugate base anion lone pair, that destabilizes the lone pair and decreases our parent compound's acidity. As a converse idea, resonance acceptors are substituents that accept electron density via resonance to conjugated atoms. Strong acceptors include nitriles, nitro groups, and sulfonates. By the same token, weak acceptors include aldehydes, carboxylic acids, ketones, esters, and amides. We can see the effect of adding resonance acceptors. For example, if we look at a phenol, which has a pKa of between 9 and 10, if we add a nitro group, which is a resonance acceptor, we see that the pKa drops dramatically to 7. To understand what's happening, let's look at the conjugate base anion for a moment. We see that when we have a resonance acceptor, we can push electron density into the resonance acceptor, and in turn, we can stabilize the conjugate base, which in turn makes the parent acid more acidic. Note that resonance effects require you to be able to delocalize your lone pair into the resonance acceptor. You may wonder why just changing the position of this nitro group has a dramatic effect on pKa. Well, part of the reason for that is when we have the nitro group in the what's known as meta position of the ring, you could take a few moments and try to push electron density into the adjacent withdrawing group. And what you can see is we cannot delocalize the lone pair into the nitro group. And as a result, this conjugate base is less stable than when we had the nitro group in the ortho position. And as a result, this parent compound, this parent acid, is less acidic. So when you talk about resonance donors and acceptors, you really have to draw out the conjugate base and check to make sure the resonance acceptor can actually function as a resonance acceptor. It has to be conjugated to the conjugate base lone pair in question. Again, a resonance acceptor must be conjugated to the anion in order to function and have an effect on pKa. For those wondering, why do we still see some effect? This is a combination of inductive effects, and even though this nitro group we aren't able to directly and fully delocalize the lone pair into the nitro group, it does affect and does impact the attached carbon atoms and can stabilize the negative charge on adjacent atoms, just not as effectively. Okay, so let's talk a little bit about anion stability trends, including resonance and inductive donors and acceptors. Sometimes groups can function both as donor and acceptor groups. So let's talk a little bit about inductive donors. Inductive donors are electron-rich atoms that destabilize anions by donating electron density. An example inductive donor would be an alkyl group. The carbonyl pulls electron density towards itself as this oxygen's electronegative, and the alkyl group can donate electron density. Why is this a problem? Well, if you're looking at an anion, this alkyl group is shoving more electron density into adjacent atoms, and this destabilizes your anion. So this anion is less stable. You can see the effect of this alkyl group because if we replace it with a hydrogen, which is a weaker donor, you end up with a more acidic compound. Why is that? If we look at the conjugate base anion, this conjugate base anion is more stable as we don't have an alkyl group shoving electron density into the pi system. If we look at chlorine, which is really a withdrawing group, we see that when we have a withdrawing group instead of a donor group, this conjugate base anion is more stable, and thus the parent acid is more acidic. Generally, the more stable your conjugate base, the more acidic your parent acid will be. There's one last effect that has to be considered. It's a minor effect, but it's important. It is the idea of solvation effects. Solvent can stabilize the anion conjugate base through ion dipole or dipole-dipole interactions. Alcohols and other acidic protons on more substituted carbons are less acidic as their conjugate base experiences less stabilizing interactions with the solvent. So for example, primary, secondary, tertiary. These names are derived from the number of substituents attached. So in this case, a primary carbon has one carbon substituent. A primary alcohol is an alcohol attached to a primary carbon. A secondary carbon, two substituents. Tertiary carbon, we have three carbon substituents. So this would be a primary alcohol, secondary alcohol, and tertiary alcohol. And as we can see, the tertiary alcohol is less acidic. Why is that? Well, if we think about the conjugate base anion for a moment, all of these substituted groups attached to our alcohol, if it's a tertiary alcohol, create hindrance. So if we have solvent, it's harder for solvent to get in and stabilize the conjugate base anion. So the solvent cannot easily stabilize the anion, and as a result, the parent tertiary alcohol is less acidic. This is a very minor effect, but it's important to note. So, in this case, let's try to identify which of the following molecules are more acidic, and I'm going to draw out the acidic proton here. So in this case, we have a proton attached to a tertiary carbon versus a secondary carbon. The conjugate base anion generated from this tertiary position versus the secondary position. In this case, we would expect, using these substitution rules, that the anion on the secondary position would be more stable, and thus this acid would be more acidic. Looking at a more classical example, we have a tertiary alcohol versus a primary alcohol. As we discussed, the more substituted your alcohol, the less acidic the alcohol will be. So the primary alcohol is going to be more acidic. Okay, let's talk about some other factors influencing acidity, and let's talk about these factors in order of importance. So, one of the major factors influencing acidity is this idea of charge. The larger the positive charge on an atom, the more acidic the protons attached to that atom are. The larger the negative charge on an atom, the less acidic the protons attached to that atom are. For example, a protonated alcohol, such as if you protonate water, protonated water or H3O plus has a pKa of around -1, while normal water has a pKa of 14. The more positive charge you have on an atom, the more acidic that atom would be. By the same token, if we look at the acidity of this parent compound, we have two protons. This proton has a pKa somewhere around 15. This proton has a pKa somewhere around 20. The moment you pull off a proton and you generate an anion, this pKa shoots up to somewhere around 35 to 40. So when you have more negative charge on a molecule, it becomes harder and harder to pull off successive protons. We can even see this with amines, where a normal amine has a pKa of around 35, while a protonated amine has a pKa of around 9. So charge has a very dramatic effect on proton acidity. The next effect that we discussed is this idea of atom electronegativity and size. Atoms, when we think about an anion, anions are more stable on large electronegative atoms. So for example, if we compare a ketone, which has a pKa of somewhere around 20, to a carboxylic acid, which has a pKa of around 4, as we can see, if we look at the conjugate base anion, placing this negative charge and placing this electron density on carbon, it's much less stable to have an anion with the electron density on carbon versus an anion with the electron density on the more electronegative oxygen. The carboxylate anion is more stable. The third major factor we discussed is resonance. If the conjugate base is stabilized via resonance, the acid is more acidic. An example of this is phenol, where this conjugate base anion can be stabilized via delocalization into the adjacent aromatic ring. This explains why phenols are more acidic. Their conjugate base is more stable. By the same token, it's important to note it's not just the fact that the lone pair is delocalized, but the atoms the lone pair is delocalized across. For the carboxylic acid, the lone pair is delocalized across electronegative oxygen atoms. So this lone pair and this conjugate base anion is very stable. And that explains why carboxylic acids are more acidic than phenol. There's one other factor that I'd like to draw your attention to, which is that the conjugate base is aromatic, follows the 4n plus 2 pi electron rule. The acid is much more acidic than usual. An example of this is cyclopentadiene, where this proton has a monstrously acidic pK of 16, which is unusual for a carbon-hydrogen bond. Why is this? We have a conjugate resonance stabilized anion, and this anion is aromatic. It has 6 pi electrons fully conjugated in a ring. This also explains why, for example, if you protonate pyrrole, this species is very acidic. Why? If we look at the conjugate base, we can see that the conjugate base of this protonated pyrrole species is pyrrole, which is aromatic. This is a very stable conjugate base, and this explains why the parent acid of this pyrrolium ion is so acidic. For pyridine, if you protonate pyridine, it is acidic, but it's not nearly as acidic because this parent acid is aromatic, and upon deprotonation, you get another aromatic conjugate base. So we don't see like a change where we're going from aromatic to non-aromatic and vice versa. In this case, both the parent acid and the conjugate base are aromatic, so there's not that much of a difference in stability. Anytime if your conjugate base is aromatic and especially stable, that means your parent acid is going to be even more acidic than usual. Okay, there are a few other factors influencing acidity, and then we're going to talk about some exceptions. As we discussed previously, inductive effects, which are electronegative groups adjacent to acidic protons, increase the acidity of adjacent protons. Classic example, acetic acid versus dichloroacetic acid. The more withdrawing groups we have, the more acidic our protons become. This also explains why, for example, when we have this nitro group in nitromethane has a pKa that's quite acidic. Looking at our table and looking at our pKa, I'd like you to take a moment to check the pKa table and try to find the pKa for a proton adjacent to a nitro group. Nitromethane pKa is somewhere around 9, so it's quite an acidic proton. The reason being is that if we look at the conjugate base anion, this anion is adjacent to this strongly withdrawing nitro group, and this nitro group is also withdrawing via resonance. One thing that it's also important to note, if we compare to, for example, a typical vinyl proton, This vinyl proton has a pKa closer to, 40. So the presence of withdrawing groups dramatically increases the acidity of adjacent protons. The next effect to consider are orbital effects. Anions are more stable if the lone pair electrons are in a lower energy orbital. This explains why alkyne protons are much more acidic than an alkane proton, because you're going from placing the lone pair in an sp hybrid orbital to placing the lone pair in an sp3 hybrid orbital, which is higher in energy. Looking at this next example for these two protonated amines, I'd like you to take a moment and consider and think about the hybridization of each nitrogen and the stability of each lone pair. This nitrogen it has 1, 2, 3 bonded atoms is sp2. This nitrogen is sp3. If we draw out the conjugate base, we see that this lone pair is held in an sp2 hybrid orbital, while this lone pair is held in an sp3 hybrid orbital. Because this lone pair is more stable, in turn, that means this parent acid is more acidic. So orbital effects do influence acidity. The last effect to consider is solvation. The less steric congestion around the acidic proton, the more acidic the proton will be. Again, primary alcohols with one substituent are the most acidic. Secondary with two substituents is the next most. Tertiary with three substituents is the least acidic. Now, although these are general rules, sometimes you encounter exceptions where multiple rules are at play. An example of this is comparing the acidity of amines versus alkynes. So if we're asked which of the following compounds is more acidic, take a moment and check the pKa values in the pKa table. An alkyne has a pKa of around 25, 26, while an amine has a pKa of somewhere around 35. This in turn tells us that the alkyne compound is much more acidic. This is a little bit unexpected, considering that we have a carbon-centered anion versus a nitrogen-centered anion. The key deal breaker in this case is the fact that this carbon is sp hybridized, while the nitrogen is sp3 hybridized. So even though this lone pair is on the less electronegative carbon atom, the orbital effects make up for this difference in this specific case. The reason why I'm showing you this exception is just the fact that you do want to be familiar with the pKa table and use the pKa table as sort of a starting point to begin to start to compare the acidity of different compounds. To this end, we can determine whether the reaction will be product or reactant favored. We can use pKa values for this. So we have a pKa of 25 for our reactant and a pKa of 35 for the product conjugate base. The delta pKa is 25 minus 35, which is negative 10, which is less than 1, which tells us that this reaction is product favored. So the equilibrium favors the products. Let's talk now about how we can apply all of this to predict the outcome of acid-base reactions. As a general rule, the reaction favors producing the most stable conjugate base and the weakest acid. You can think of it as the fact the strongest acid reacts to readily push the reaction equilibrium to the opposite side. So for example, if you have a carboxylic acid and an amine reacting, the carboxylic acid with a pKa of 4 is stronger than the protonated amine with a pKa of 9 to 10. Further, if we think about conjugate base stability, the carboxylate anion is a very, very stable conjugate base. So this equilibrium massively favors the products. Let's do some case studies now, where we predict the outcome of acid-base reactions. So here we're asked to determine, is the following reaction reactant or product favored? I'd want you to list the pKa's for each acid. This reaction is actually a very common set of reaction conditions, which is used to make what's known as an enolate anion. So you'll see this exact set of reaction conditions later on. So you may want to pause the video, take a few moments, and then we'll discuss this example momentarily. So thinking about pKa values, the pKa value of an ester is somewhere around 30. Well, actually, it's closer to between 25 and 30. The pKa of an alcohol, even a tertiary alcohol, is around 17 to 18. From this, if we calculate the delta pKa, so we have 25 minus 17, that gives us positive 8, which is greater than 1, which tells us that this is reactant favored. So the equilibrium more favors the reactants. We can also deduce this looking at the conjugate base anion. Here we have an anion centered on oxygen. Here we have an anion centered on carbon. Using our electronegativity rules and considering atom effects as the major contributor, this anion with a negative charge on oxygen would be the most stable conjugate base anion, and the equilibrium thus favors generation of this more stable conjugate base anion. Again, the equilibrium favors generation of the weakest acid and the most stable conjugate base. Let's look at another example. This time we have an alcohol. In this case, we have an alkoxide anion reacting with phenol. So pause the video, take a few moments to look up the pKa values, and I'd like you to tell me whether the following reaction is reactant or product favored. Okay, so phenol has a pKa of around 9. This secondary alcohol has a pKa of around 17. So if we think about it in terms of calculating the difference in pKa, 9 minus 17 gives us negative 8, which is less than 1. So this reaction is product favored. This makes sense. Phenol is the strongest acid. The alcohol is the weakest acid. And this resonance stabilized anion is the most stable anion. So the equilibrium favors the products as the products contain the most stable anion and the weakest acid. Okay, let's talk a little bit about drawing acid-base reactions. This is going to be your first introduction to mechanisms. So acid-base reactions involve the transfer of a proton from the acid to the base. So to draw proton transfers, you're going to draw an arrow starting from the basic atom's lone pair to the acidic hydrogen. You're then going to draw a second arrow from the acidic bond attached to your proton. So this XH bond is the bond attached to the acidic proton, and then you're going to draw the arrow from this bond to the attached atom X. You're then going to draw the conjugate acid with the new base hydrogen bond and draw the conjugate base with a lone pair. So for example, if we're drawing a proton transfer between this anion and an alcohol, the anion lone pair is going to attack the acidic proton. So we draw an arrow from the lone pair to the acidic proton. And then we draw a second arrow, breaking our oxygen-hydrogen bond and generating a lone pair on oxygen. This is why we end up with an extra lone pair and a negative charge on the conjugate base anion, and how we have a new nitrogen-hydrogen bond in the product. Net, a new base hydrogen bond was formed using a lone pair, and the acidic hydrogen bond was broken to give a new lone pair. So let's practice this. I'd like you to take a moment and practice drawing out the acid-base reaction between this methoxide anion and nitromethane. So in this case, the methoxide is going to pull off your acidic proton. We break the carbon-hydrogen bond, and that generates a lone pair on carbon. We also form an oxygen-hydrogen bond, and that gives us methanol. Perfect. So let's practice now, and let's do some more practice. So I'd like you to take a moment, pause the video at this time, and work on drawing a mechanism for the following reaction. I'd also like you to tell me, is this reaction reactant or product favored? So let's take a few moments and we'll discuss momentarily. So first and foremost, we have our basic anion. It's going to pull off a proton from water, break the oxygen-hydrogen bond to generate a new lone pair. That gives us a new carbon-hydrogen bond and a new conjugate base anion, where we have an additional lone pair on this oxygen atom. Where did the lone pair come from? It came from the oxygen-hydrogen bond electron pair. So let's now address whether this reaction is reactant or product favored. First and foremost, this alkoxide anion, let's list the pKa values. The parent alcohol has a pKa of somewhere around 17. This beta keto ester pKa, this is a bit of an unusual functional group. But we'll see it a lot in Chem 113 and in the later parts of this class. The beta ketoester is much more acidic than usual and has a pKa of somewhere around 12 to 14. Now, based on these pKa values, if we look at the difference in pKa, so if we take 17 minus 12, that gives us positive 5. And that tells us that this overall equilibrium is reactant favored. In other words, we can also figure out the directionality of this reaction by thinking about anion stability. This anion is a stable anion. It is stabilized via resonance and conjugation to multiple electronegative atoms. Because this anion is especially stable, even though this anion is centered on carbon, this anion is more stable than the alkoxide anion, which just places a lone pair on oxygen. This is another example of resonance and conjugation effects overcoming atom effects. In terms of how to approach these problems, I would encourage you to draw out the conjugate base anion and the parent base anion. Think about the factors that can influence the acidity. And if you're stuck, you may want to reference and be familiar with common pKa values to help determine whether the reactant acid or the conjugate acid is the stronger acid. and thus whether the reaction is going to be reactant or product favored. You can do it via pKa values, quantitatively, or qualitatively, thinking about anion stability. We're now going to talk about a subclass of acids and bases, Lewis acids and Lewis bases. So Lewis acids and Lewis bases are very different from Bronsted acids and Bronsted bases, but they're very relevant for organic reactions. A Lewis base is a lone pair donor or pi bond donor. So for example, an alcohol can donate a lone pair, while an alkene can donate a pi bond. A Lewis acid is a lone pair acceptor. Many Lewis acids have an available empty p orbital. An example of this is aluminum trichloride, a carbocation. H plus is also a Lewis acid, and carbonyls and other groups containing pi bonds where you're attached to an electron withdrawing group can also be considered Lewis acidic in some cases. Now, Lewis acid-base reactions are pretty interesting, and this is the idea of coordination, where the Lewis-base lone pair coordinates with the Lewis acid to form a complex. So when we have our Lewis base, which is a lone pair or pi bond donor, the lone pair is going to attack the Lewis acid, which has an empty p orbital that can be attacked, and we're going to form a bond using the Lewis base's lone pair. This yields a coordination complex. And one thing that's occurring in this process is you're making this compound much more reactive with nucleophiles and other electron donating species because this oxygen now has much more cationic character, and in turn, the carbon attached to the oxygen is much more electron deficient than usual. Which means that if you have anything with an available lone pair that can attack this carbocation, overall, when you have this Lewis acid coordinating to your Lewis base, you activate the Lewis base for further reaction. So to practice this, I'd like you to indicate the Lewis acid and Lewis base in the following reaction, and I'd like you to use arrow pushing notation to show the coordination of the Lewis acid to the Lewis base. So take a few moments to work on that, and then we'll discuss. So here in this case, we have boron, which is going to be the Lewis acid. BF3 is a very common Lewis acid. Boron has an available empty p orbital that can be attacked. This epoxide oxygen will be our Lewis base, which is going to be the lone pair donor. It's going to attack the Lewis acid, and that's what forms this oxygen-boron bond. Okay, the last thing we have to talk about, and this is very important, is that in a practical sense, we run organic reactions in solvents. Reactions are run in a solvent, which is an organic compound that usually dissolves the reaction components. The solvent is capable of potentially reacting with acidic or basic reagents. And this can be intentional in some cases. And because of this, we have to consider what's known as the leveling effect. The strongest base that can be present in solution is the conjugate base of the solvent. The strongest acid that can be present in solution is the conjugate acid of the solvent. Why is that? If you have a base and you have a solvent, the solvent can react with many acids and bases to generate the conjugate base of the solvent. By the same token, an acid can react with the solvent to generate the conjugate acid of the solvent. Now, in some cases, this can be done intentionally, but you really have to be careful when picking your solvent to not trigger an undesired reaction. So, to avoid undesired reactions, make sure your solvent has a higher pKa than the conjugate acid of any bases used in the reaction. If the solvent is more acidic than your reagents, your solvent is going to be deprotonated. For example, if you have the idea to run the following acid-base reaction, but you run it in nitromethane, which is our solvent, you may think, oh, I just have to draw this acid-base reaction. My base is going to pull off a proton from this acid, and all will be right. However, nitromethane has a pK of around 9. This ester has a pK of around 25 to 30. So rather than going after the ester, your base is going to pull off a proton from the solvent. And that's why you end up generating the conjugate base of the solvent in this case. So please be careful when you check the solvent and you pick the solvent that the solvent is not capable of interfering with your chosen acid-base reaction. Note, this can also be leveraged intentionally. Some reactions explicitly react the solvent. An example of this is reactions run under equilibrating conditions will generate a solution of the solvent and its conjugate base for reactions. For example, if you treat the following diketone with sodium hydride in tert butanol, what will happen is the tert butanol will react with the sodium hydride and generate tert butoxide. And it's this tert butoxide that's actually functioning as the main base in this acid-base reaction. Why do we go through all this effort? These conditions in particular are very helpful to more gently generate a conjugate-based anion, and we'll talk more about equilibrating conditions in future chapters. The key thing I want you to take away with, the solvent must be considered, and the solvent can participate in acid-base reactions if your reagents are sufficiently basic or if your solvent is sufficiently acidic. So this concludes our lecture for chapter 2, and we'll continue on with future chapters in the next of this lecture video series.